Yes. How's it going, guys? So I got problem number 4, and that starts by saying that a rocket from SpaceX burns the fuel at a rate of 10 kilograms per second, expelling its gases at a relative speed of 5 kilometers per second. And this is the the speed relative to the rocket. Okay, so the first question A on the first part, it it's asking to model the fuel burning as a steady ejection of small pellets, each with a small mass of delta M. Okay, so for this we have to consider the mass of a pellet, which is delta M. Okay, so here we have to think about the fuel, and well, usually in this case, this rocket would start with a mass of M0. We're just gonna denote it as M naught, which is the initial mass of the fuel. Okay, so this fuel, which is our initial fuel, the initial mass of the fuel, is gonna decrease by a certain amount of pellets the rocket burns. So we can say that it burns, I don't know, maybe 5 every second, 10 every second, but that doesn't the problem doesn't really specify that, so we're gonna say that it burns, oh, sorry, burns an n amount of pellets every so often. It doesn't we don't really have to include time in this case. Okay, so our mass, the mass of the rocket, would be best described as a function of the amount of pellets it has expelled. So m of n would be our initial fuel minus the amount of pellets it's been expelling at that certain moment. Okay, and I think this is the answer to our first question. There might be many other ways to model the mass of the fuel, but right now we're not really given any of those details. Well, we can say that it's someone could say that maybe the 10 kilograms per second would work, but it doesn't really tell us that each pellet is maybe 5 kilograms, 10 kilograms, maybe even 20. In that case, it would be one half of a pellet every second. Okay, so I think this is a better representation of the fuel burning. Okay, so for part two, uh, it's asking. It says that it takes a short time t. So I'm gonna put part two, a still. It takes a short amount of time, which is denoted as delta t, to accelerate a pellet, and this is at a constant acceleration, uh, to to the exhaust speed, which is Vx. So we can represent that clearly right here. So we have our pellet expelled right here, and it it ends up with a velocity of Vx, and this in a time t delta t. Okay, so if the rocket is held in place, that means that it stays in the same position, so it doesn't recoil. So we could just hold it right here, put an imaginary wall here, and it keeps burning fuel. It's um, trying to get up get out of that wall, but it's not allowed to because the wall might be like very strong. I don't know. Okay, so it's asking for us to find the magnitude of the force a pellet exerts on the rocket during the short amount of time. So this thing right here, force applied. We can also say force of pellet, which I think would be a better idea. Okay, 1 second. Okay, so in this case, well, we know that from Newton's second law of motion that the force on any object is going to be the mass of that object times its acceleration. And here, we don't really have an acceleration, but we have a change in velocity. And this is right here. So it's gonna end at a certain speed and that amount of time, but we have to think that. Whoops, I'm so sorry for that. I was calling on well, one more time. So we have to think that the pellet was it had an initial velocity of 0. It was at rest, and then that it was exerted, it was used, I guess, and then its final velocity was VEX. Okay, so now one more thing, we can also represent this as m or dv dt, which is its the definition of acceleration, just a rate of change in velocity. But since we're not really dealing with infinitesimally small changes, we're just gonna try to approximate it as f equals m delta v delta t, which is reasonable in this case. And we can find delta v and delta t in the rate of change of velocity with respect to time. Okay, so for the pellet, in this case, well, we can actually say pellet is equal to mass of pellet times acceleration of pellet. In this case, the rate of change for the pellet is going to be its final velocity, which we already know is going to be Vx minus its initial velocity. And since we know it started from rest, this is just going to be 0. And the units are here meters per second. And we know that it was exerted that it took a time of delta t to accelerate that pellet. It doesn't really give us any more details, so we're just gonna leave it like that. So in this case, Vex minus 0 is just gonna be Vx over delta t. And this is in seconds. So we can see that we have units of acceleration. Okay, now one more thing. We know that the mass of each pellet from the previous part is just equals to delta m. So in this case, the force of our pellet just going to be delta m times the rate of change of the velocity or the acceleration. So we're right here, we're just going to approximate, and we're going to put Vex over delta t. Okay, and this can be represented as Vx delta m over delta t. And so this would be the magnitude of the force. Now, we know that this is going to be Ed because of Newton's third law of motion, which just states that for every action there's always an equal and opposite reaction. So if it went down on this way, then that means that it had an effect on the opposite direction. Okay, so this is just gonna be the force, well, the magnitude of the force in this case. Okay, and so this is for second part on part A. Okay, so now we go on to part B. Okay, so part B, if the rocket is moving at VEX, oh, it's moving. I'm sorry. So that means that this is moving. So we get rid of the invisible wall. So this is moving. Um, okay. Then VEX is no longer the pallet's speed through space, but relative to the rocket. Okay, there we go. By considering the limited case of 0m of delta m and delta t approaching 0, which would we interpret as the rocket's burning full continuously, calculate the thrust for the values given above. So we have to think in this case of pellets. The thrust in this case is just going to be the force provided by each pellet onto the rocket. So basically this. But now we're burning um, we're burning pellets continuously, and this is, as we already mentioned, this is just an approximation. So we just go back to our definition of the force. So the force of the pellets is going to be as we have the velocity Vx times, now we are burning continuously, so we're going to use our differential dt. Okay, and this is going to be our force of thrust, since we know that the thrust is the force exerted, well, the force provided by each pellet continuously onto the rocket. Okay, so now we have this and we have this, and this is just what's just given in the problem. So the rocket burns fuel at 10 kilograms per second. This is a rate of change of mass with respect to time, and we also have our speed, which is our VEX. So we just plug this in. Force in this case, since it is continuously, then this becomes thrust. It's just going to be our velocity, which we said was 5 kilometers per second. That's very fast. Times our change in mass. So this is burning fuel at 10 kilograms per second. Okay, so this we can calculate it. This is 5 times 10, which is just 50. We have units of kilometers times kilograms divided by seconds squared. Now this is not our units for force. We have to convert the kilometers into meters. So we can put 1 kilometer is equal to 1,000 meters, and 1,000 can be represented as 10 to the 3 meters. Now we see that the kilometers cancel, and we're left with units of meters. So we have 50 times 0.0, 10, 10 to the 3 newtons in this case. But for keeping our sig figs, we're gonna put 5.0 times 10 to the 4 newtons. And this is the force of thrust. Well, that's a lot. And that's the force of thrust. So there you go. We have it, everything. And this is for problem number 4. Thank you guys.